Thank you, Caitlin, for the introduction, and thank you everyone for taking time to join this session. I'm very happy to be able to share with you some of the research that we've been doing at Cloudera Fast Forward Labs relating to learning with limited label data. But before I do that, I just wanted to spend some time to introduce ourselves, tell you a little bit about who we are and what we do. At Cloudera Fast Forward Labs, our goal is to bridge the gap between research and machine learning and industry applications. And one of the ways we do this is through publishing research reports. These reports are meant to highlight an emerging capability within machine learning that we believe will become important for the business community within the next 6 months to 2 years from when they're published. Here are a subset of reports that we've worked on in the past. They include topics related to languages, images, probabilistic systems, and obviously deep learning. The other mechanism that we use to essentially close the gap between research and application is our machine learning application development. In these projects, we essentially consume our research and use it to enable our clients to become more innovative and efficient in their business processes. So today, I plan to do 2 things. First, I will walk you through our report on learning with limited label data, which I led, and I will also walk through the prototype that we built for this report. The second portion of this talk will focus on transfer learning, which is closely related to learning with limited label data, and we'll talk about transfer learning for languages. So let's get started. Supervised machine learning is powerful because it allows us to teach machines using examples, but these machines need many, many examples. So for the medical use case, unless all of these images have a proper label, we cannot actually use them to train a model. Those of us who work with data in real life know that real life data doesn't always come nicely packaged with labels. It's messy and very unorganized. We actually might have a lot of data, but it's hard to leverage them to build anything useful for the enterprise. Take financial institutions, for example. Risk assessment is crucial because that determines the amount of capital that needs to be set aside to absorb systemic financial risk. Volumes and volumes of loan documents and contractual documents exist and can be used to build a risk model. But then not very many of these documents have been properly processed to extract information such as the loan amount, the loan type, the loan purpose, the collateral amount, and so forth. In healthcare, medical images are abundant and can be used to build a diagnostic model. But once again, these images have also not been properly labeled. For corporate IT, chat logs are widely available and can be used to understand customer complaints, customer satisfaction, and customer preferences. But once again, these chat logs have also not been processed properly. So what should enterprises do to leverage this large pool of real-life data that they're sitting on? One approach, it's a brute force approach, is to really just manually create labels for everything. This is very inefficient, very expensive. It is doable, but there has to be a better way. Can we use some kind of intelligence to help us identify which data points to create labels for? Can we actually only create labels for data points that will be helpful for the model? Can we build a model using this small set of labeled data and have it perform almost just as well when you compare to a model that we would have built using the much larger labeled data set? So it turns out the answer is yes. With active learning, we can take advantage of the collaboration between machines and humans to only smartly select a small set of unlabeled data to create labels for. We can then build a machine learning model using this small set of labeled data. Now, this capability opens up new product possibilities that were previously constrained by limited labeled data, and also allow enterprises to take advantage of this large pool of unlabeled data that they have. Active learning is actually not new, but it only has been recently adapted to deep learning. Along with a maturing ecosystem and availability of tooling, we think active learning is actually newly exciting. So let's take a look at how it works. You start with a very small set of labeled data. You use this to build a machine learning model. This model is then used to make predictions across your entire pool of unlabeled data. Now, in the process of making prediction, the model also picks out data points that it has the most difficulties with. The human then steps in to provide the label. This data point becomes a labeled data point, and we can add it back to our original labeled data pool and restart the process. So active learning looks like an iterative process, and if it's working properly, this is what you should expect to see. Over rounds and rounds of active learning, as your number of labeled data point increases, you should observe a general uptrend in model performance. Now, this improvement does not have to happen over each consecutive rounds of active learning, but if you observe it over a long run, it should be obvious. Then the next question is, if it's iterative, how do I know when to stop? Each data point, each labeled data point, actually has a cost of acquisition. That is the amount of time and money we spend to label it. Now, some data points are very easy to label, some not so straightforward. It's easy to label an image as a cat or a dog, but not so straightforward to label an image for automotive insurance claims for damage severity. It takes much longer, and it requires domain expertise, which is expensive. With that cost of acquisition in mind, we can think of the stopping criteria as either a dynamic criteria or a static criteria. The static criteria is straightforward. So at the beginning of the active learning cycle, you set a budget arbitrarily, or you set some kind of model performance target arbitrarily. And you just kind of continue the active learning cycle until you hit either one of those metrics. For example, I could say at the beginning of an active learning project, I would say, let's just limit our budget to be $10,000, or let's just arbitrarily say, I want to stop when my model hits 85%, some kind of metric. This is arbitrary, so a better approach, obviously, is to think about a dynamic approach where you're looking for the incremental improvement over each round of active learning, and you stop when an additional round of active learning doesn't return a lot of performance improvement. So that's the basic setup of active learning. At the heart of active learning is the model's ability to pick out data points that it has difficulties with. How does it do that? It turns out the model uses a selection strategy. Now, the simplest strategy is really to have no strategy at all. I randomly select data points to get labels for, and this has a name. It's called random sampling. You can think of it as picking the top card from a shuffled deck, requesting a label for that, reshuffling the deck, and then picking the top card and requesting labels for that. Now, random sampling will guarantee you more data, more labeled data, but not necessarily the best set of labeled data. But it's actually still useful for two reasons. First, when you have no labels to begin with, random sampling is the way to go, because it will allow you to get to a small set of labeled data upon which you can then apply this active learning process. The other great thing about random sampling is that it is an awesome baseline. It's so simple, so everything else that's more sophisticated should perform better. So we love it for these two reasons. Now, earlier I said that these models pick out points that it has difficulties with. So points that are difficult can be thought of as points that the model is uncertain about. And one way to quantify uncertainty is to use the notion of margin sampling. Let's use an example. Assume I'm trying to build a very simple classifier to classify reviews into positive or negative reviews. And assume that my classifier gives me a very nice linear decision boundary as shown in pink. And assume that my model only takes in two features, the number of positive words and the number of negative words. Now, everything to the right of this decision boundary will be classified as positive. Everything to the left will be classified as negative. Now, points right around the decision boundaries are the ones that the model is most uncertain about. And why is that? Any small changes in model refinement due to model refinement will cause those same points to be classified differently. The model's not quite sure how to classify them. But if we move very far away from the boundary, small changes in this boundary will actually not change the classification. So the way we use margin sampling and active learning as a selection strategy then is to compute the distance between the data point and the boundary, and then we pick the one that's closest to the boundary to get labels for. Knowing labels for those data points will help the model become better. Another way to measure uncertainty is to use the notion of entropy. Some of you might be familiar with entropy. It is really just a way to formalize the intuition that outcomes of uncertain events carry more information than outcomes of certain events. Let's see how that's true using this coin toss example. The maximum entropy of a coin toss is 1. And when does that happen? That happens when we're tossing a fair coin. When you toss a fair coin, you don't really know what you're going to get. With equal likelihood, you will get a head or a tail. So it's a very uncertain event. The entropy is 1. Now, imagine you're tossing a double-tailed coin. Is there any uncertainty in the event? Not quite, right? Because you know you're going to get a tail. The entropy is 0. If you're tossing a double-headed coin, you're going to get a head, so the entropy is 0. Now, how do we use this notion of entropy in machine learning models? Now, imagine I'm trying to build a model to classify one data point into 10 categories. And let's say I built 2 models. The first model will tell me that this data point will be equally classified into each of the 10 classes. So the probability is 0.1 for all of the classes. The second model will say that, hey, this data point will be classified very strongly into one class, 0.9, and then very unlikely into all the other classes. In this case, which entropy is higher? The one where the model classifies equally into 10 buckets, that probability distribution will have a very high entropy. Essentially, that's reflecting the fact that the model's uncertain. I'm not sure which one, so I'm going to classify equally into 10 buckets. So we can use that as a way to measure uncertainty for machine learning models. And we use that uncertainty to help us select data points. And the way we do that is we'll take a small set of data points to build a model. We use that model to output prediction probabilities for all the unlabeled data points. We compute entropy for each of the probability distributions, classifications for all the unlabeled data points, and then we pick the one that has the highest entropy. Those are the ones that the model's uncertain about. Those are the ones that we should get labels for. So the 2 approaches that I mentioned before are actually classical selection strategies. It turns out they don't work very well for deep learning for 2 reasons. First, deep learning trains in batches and is very, very data hungry. A couple of newly labeled data points really doesn't help it much. Second, deep learning is highly, 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 highly high dimensional. And all these heuristics that we use classically actually doesn't translate very easily over to the domain of deep learning. And we'll take a look at one example. Let's go back to margin sampling. In margin sampling, if you remember, what we're trying to do is compute the distance between the data point and the decision boundary. This computation is not doable for deep learning models because we very often don't know what the boundary looks like. It's too high dimensional. But what we could compute is this, the distance between the data point and the closest neighbor of a different class. Now, even though this computation is doable, it's very, very expensive. And it only gives us a very coarse estimate of the distance that we're actually looking for. So let's do something fun. Let's use perturbations. Adversarial perturbations could be used to estimate the distance. And let's first define what these perturbations are. When you add a small noise to an input of a deep neural network, and when that causes the input to causes that particular input to be misclassified unexpectedly, that's essentially a perturbation. So if you look at this image, we add a small noise to an image of a panda, and it ends up being classified as a gibbon. To the human eyes, it looks exactly the same, but to the computer, it's now no longer a panda, but a gibbon. So how do we use this? The idea then is to compute the smallest magnitude of perturbation that will cause an image to misclassify, or an input to misclassify. Now, when this misclassification happened, the input essentially has hit the decision boundary, has hit some boundary, causes it to change classes. So then we can use the magnitude of the perturbation as a way to estimate the distance to the boundary. This is a fun way to do things, but this can also take a while because we have to compute perturbations for every unlabeled data point, and depending on what kind of perturbations we use, it could take a while. And in our report, we talk about other approaches to measure uncertainty in deep neural networks, including the dropout approach and the ensemble approach. I want to switch gears now to do a little walkthrough of the prototype that we built for this report. Hopefully that will make everything clear. Okay. Okay, so this is the prototype that we built for the active learning report. It's called Active Learner, and it's publicly available at activelearner.fastforwardlabs.com. The goal of this prototype is to illustrate the process of active learning, and hopefully, in the process, provide some intuition as to why and how it works. We do it by using 3 different data sets. You see the 3 different data sets on top. The first one is MNIST. That I don't think needs any introduction. Is the Hello World data set for machine learning and data science. It consists of a series of handwritten images from 0 to 9. And just to show you what they look like, here are some 7s, here are some 2s, here are some 1s and 8s. The second data set that we tried is the Quick Draw data set. It consists of a series of hand doodles. The original data set has 345 categories. We randomly selected 10 for the purpose of this prototype. The 10 categories that we ended up selecting are dolphin, cat, face, angel, airplane, apple, broccoli, crayon, bicycle, and elephant. And just to give you a sense of what these images actually look like, here are some apples. Here are some broccolis, and here's a dolphin. It took me a second. All right. So the last data set is the most realistic data set. It consists of real-life images. And the original data set has 256 categories. We randomly selected 10. And they are at the bottom here: cake, dolphin, elephant, bridge, goldfish, rainbow, teapot, teddy bear, washing machine, and waterfall. And here's what they look like. Here's an elephant. Here's a bridge. This is a fish. Okay, so I'm going to go back to MNIST. And on these data sets, we built a model to classify the data into 10 categories. The number of categories remain the same across different data sets. And we use different selection strategies to try to figure out which data points that we should create labels for. And the different strategies that we used are random strategy, entropy. Entropy is what I mentioned earlier. It's a classical selection strategy. It works great for non-deep learning models. Adversarial and ensemble are 2 approaches that specifically work for deep learning. And so over here, we're trying a baseline, something that works for non-deep learning and something that works for deep learning. Here, at the bottom corner here, are really just numbers and stats that help you keep track of what's going on with the active learning process. And what is this blob here? These are actually embeddings that we grab from the model that we built for each of these different data sets. And then we grab the embeddings and pass it through a UMap, which turns it into a 2D visualization, which we then display on this plot here. So let's take a look at how active learning works. And we'll start with the simplest data set, which is the MNIST data set, and using the simplest strategy, a random selection strategy. Actually, let me restart this so we start from the beginning. Sorry about that. Okay. All right. So for those of you who are familiar with MNIST, we have a total of 60,000 training data points available. Those have labels. But for the purpose of this prototype, we're just going to assume that we have 5,000 data points that are labeled and everything else is unlabeled. We use this 5,000 data points to build a model, a ConvNet, and then we get an accuracy of 92.3%. We use a selection strategy, random selection strategy, to help us identify the next 1,000 data points to create labels for. The ones that are identified are grayed out, so all these gray patches that you see here are the data points that the model is asking for labels. Now, because this is a random strategy, you see that these data points are scattered all over. So let's just say I have now managed to create labels for these 1,000 data points, and I use it in my next round of training. My next round of model now has 6,000 data points to work with, and then the model improves to 94%. And then these are the next set of 1,000 data points that it's requesting labels for. Now, what if I use a better selection strategy? What if I use something that I know will work for deep learning? Let's try the ensemble. The first thing you see is that the data points are no longer randomly dispersed. They're actually kind of clustered around the edges of these blobs. Now that makes sense because the goal of the model really is to separate out these clusters, right? If we have a perfect model, we should see 10 blobs. So knowing information about the edge, data at the edge of these clusters, will really help the model become better. So we will provide these data points, and then in the next round, the model has now 7,000 labeled data points to work with, and then you kind of just go ahead. And you should see better separation as you go forward. Okay, so that is for a simple data set in MNIST. And if you notice, we've only used 8,000 labels versus the 60,000 available, and then you can still get to an accuracy of 97%. So that just shows that not all the data point is useful, not all the labels are useful. If we can pick the ones that are, or has more signal to the model, that will be even more beneficial. Okay, so let's take a look at a different data set. This is slightly more complex. This is the quick draw data set. Okay. The same thing with quick draw. We have available 65,000 labels. For the purpose of this demo, we assume that only 5,000 are available and build a model using that. You will first notice that the accuracy of this model is quite low, is 76% compared to the MNIST model. And that just shows you how much harder this data set is and how hard it is to know how big the initial data set has to be, right? Our thinking is that it should be at least better than random. If you have something that's better than random, based on how many classes you're trying to classify into, then that itself is promising. So let's go to the next round. Let's try an ensemble approach. What you see is that it's asking for data points right in the center of this blob. It also makes sense because this blob hasn't even been separated out. So it's really trying to target the center. If I know more information about these data points, the one that's grayed out, maybe it will help me build a better model. So let's assume that we've collected labels for all these. We go to the next round. And then you see some separation. So you can play with this. This is publicly available. I'm going to keep the Caltech for your own enjoyment. So let me go back to the slides for now. Okay. So hopefully at this point, we've kind of agreed that active learning is tempting. It allows us to build model using a small set of labels, and it sometimes allows us to get to these models much faster. So what's the catch? With active learning, it turns out you have to make a decision as to the type of learner to use and the type of selection strategy to use at the very beginning when you have only a small set of labeled data. The learner is used to make predictions across your entire pool of unlabeled data. And selection strategy then steps in to say, these are the data points that I need labels for. And then it keeps on going. Now, choosing a learner in general is a hard problem in machine learning, but it's made even harder in the setting of active learning because we have such a small set of labels to work with at the beginning. The other thing that makes it hard is that the learner is not just used to make predictions, it is used in conjunction with the selection strategy to help refine itself. So this tight feedback loop essentially amplifies the effect of a wrong learner. Typically, what we've seen is that when you do apply this, sometimes people don't use one single type of learner. They use a linear and a nonlinear. Essentially, you try to combine it such that your label data pool doesn't get tied to a particular type of learner. Let's just say we have managed to pick the right learner, then what is the effect of these strategies? For some selection strategies, you will end up with a set of label data point that's very biased. If you look at margin sampling, what it's doing is asking for labels right around the decision boundary, so the pink dots that I've shown here, and it's building a model based on that. Now, data points very far away sometimes is not even looked at when we build a model. So what we're building a model on is actually maybe using a data set that's not very representative of our original data set. It's very important to then understand the effect of these selection strategies on your data set and pick one that works. And how would you know? You actually have to step up slowly. You start from a random, and then you go from a slightly more sophisticated strategy, and then you go on from there. But I would say that the entropy approach for non-deep learning has been shown to work best for many, many scenarios. The last implication of active learning is that because it requires humans to provide labels, it is actually restricted to certain use cases. So humans can label images and text, but we cannot tell from a set of transactions whether it's fraudulent or not. So active learning cannot be used for that use case. In addition, because a human has to step in to provide labels, and these labels are by definition harder and more uncertain, it is very easy to introduce human biases. It's very easy under this type of circumstances to essentially inject our own bias and judgment into making labeling decisions. And what we've seen is that sometimes in applications of active learning, what people generally do is they have a panel of annotators, and then they make labeling decisions based on majority rules. For those of you who are interested to learn more about active learning, we have a bunch of resources available. The first one is our prototype that I just showed. It's publicly available at activelearner.fastforwardlabs.com. We have a series of blog posts on our website. The first 3 relates to active learning. There's an intro, which is a guide to learning with limited label data. There's an invitation to active learning, which allows you to play with some tool that we have online. And there is also one on visualization of active learning. The next one is on meta learning, which is also a way to learn with limited label data. And the last one is a blog post on weak supervision using Snorkel, along with code that you can play with. For a more, maybe a little more technical treatment of this learning with limited label data topic, I did a TWIML recording, and you can find it there if you're interested. So that's active learning. Let's move on to transfer learning for languages. Transfer learning is obviously one approach that you could use to learn with limited label data. I think many of you might be familiar with transfer learning for images, but transfer learning for languages has only been recently made possible. Automatic language understanding is difficult. For a machine to be able to do sentiment analysis, it has to get all these things right. The first sentence, this car is a pleasure to drive, it has to recognize that it's positive. The second sentence, this car is hardly a pleasure to drive, it has to understand negation, and it has to know that this is negative. The third one, this car is hardly cheap, but it was a pleasure to drive. If you're trying to classify them into good or bad, it's hard to say, because I can't tell from this if it's a good or a bad classification. Next 2 sentences, this pillow put me right to sleep, it's a positive sentiment. The next one, this movie put me right to sleep, is negative. So the machine needs to understand the meaning of words. It needs to understand negation. If we're trying to route customer inquiries, the machine needs to understand that certain words actually might mean different things. I need to make a deposit to my online banking account. This one, the word banking means actual banking, and it should be routed to a banking department. The next sentence, I was banking on my new credit card arriving today, but it's not here. Now, the word banking here means totally different things, and the machine has to know that this should go to the credit card department. It is possible to build a machine learning model, NLP model, to solve each different task separately. But this is very expensive. Technically, it's doable, but we need a lot of data, we need a lot of infrastructure, and we also need a lot of machine learning experts. But we could leverage transfer learning, and when we do that, this brings down the cost and complexity of deploying these models. In transfer learning, you build a model once, and you use it for all your different tasks. Is transfer learning completely new in NLP? Not really. We've been doing transfer learning with embeddings or word vectors. So let's figure out what these are. Some of you, I think, are familiar with it, but for those of you who are not, embeddings are essentially a mathematical representation of words that carry meanings. So it is just a bunch of vectors. But what happens is that it tends to group things that have similar meanings together. So on the top right-hand blob, you would see kitten, cat, dog, puppy. They're grouped together. At the bottom right-hand, you'll see dwelling, house, home. They're also grouped together. And these are just grouped based on the vector representation of words. And over here on the left-hand side are just a bunch of cities and countries. How do we use embeddings right now to transfer learn within NLP? And the process looks like this, and it's pretty standard at this point. You take an existing trained word-to-vec model, so these are embeddings, word-to-vec GloV, for example, and then you just put it into your model. The model typically follows fixed steps. So the model typically has, it will take in the sentence, it will tokenize it, and then it will convert the token, which is still words, into numbers. And the way you do that is through these token embeddings, or word-to-vec GloV embeddings. And then once you've turned words into numbers, you can then build a predictor out of that. Does this work? With that type of transfer learning, you do see a huge leap in terms of performance if you compare it to other approaches. But word-to-vec is actually too simple because it doesn't have context. Be careful not to slip and fall. The leaves are beautiful in the fall. Fall means two different things in these sentences, but if you look at a word-to-vec representation, they're exactly the same mathematical numbers. So to make transfer learning more efficient for natural languages, what we essentially need is a better representation. We need a representation that can understand negation, that can understand entity, that can do co-reference resolution, and then can do dependency parsing. How do we find such a representation? What tasks should we train the model on that will capture all this ability? Do we have the data to do it? Is it too technically difficult? The aha moment within the NLP community is that language model is actually the right thing. And why is that? Well, let's first define what a language model is. A language model is really a model that helps you predict the next most likely word. If you look at the sentence, the best pizza is from X. A language model will tell you with some probability it should be New York, with some probability Italy, Chicago, Detroit. The most likely word is Chicago, so the best pizza is from Chicago. We will agree or disagree, but let's not do it here. So why is language models so great? Because this is actually not hard to train, so technically it's possible. But most importantly, the data is easily available. When you train a language model, all you need is a huge corpus of text, and the label for the model is actually within the text, because you're looking for the next word or the word before. And does language model actually capture all the things we want it to capture? Turns out, to be able to build a good language model, we have to understand a lot of things. We have to have a deep understanding of the language. We have to understand the context. We also have to be able to understand negation. So take a look at this example. The coffee here isn't bad. It was actually really something. Now, For the language model to say enjoyable, it means that the language model understands negation. And negation, as we've seen before, is something that's very important when we're trying to build a sentiment analysis model. The coffee here isn't bad is actually a positive sentiment. There are various types of language models. Some are forward language models, so you predict the next word on the right. Some are backward, you predict the word on the left. And you also have ones that combine both front and back. With that, this is what your pipeline looks like for natural language processing with transfer learning. You take in a sentence, I really love this movie. You tokenize it into words or subwords. Over here, we're showing words. I really love this movie. Now, this is a word that you then convert into a number using the token embedder. The token embedder is just a word-to-vector. And then you add another layer, which is the contextualized token embedder. You pass that through this layer. Now you have some number that actually understands context. So the word fall as a season and fall as an action will have different mathematical representations. Now with that, you can then just tag on the predictor that you have already to either predict ratings or sentiment or whatever you want. So what we did during our research is essentially test out transfer learning and see how well does it work. We did it by building a prototype called TextFlix. It's also publicly available. You can find it at textflix.fastforwardlabs.com. It is a sentiment analysis tool that allows you to look at movies out of the IMDb movie review database and then see how the sentiment, what the sentiment is for each movie. And you can rank it by the mostly highly rated by sentiment or vice versa. But what we thought was interesting was to really try to see how much training data do we need when we have the ability to do transfer learning. And to test that out, we used two different models. One is a baseline. The baseline is just pretty much a bag of words. It's a naive Bayes approach. And then the state of the art is the BERT large. Now, these models are easy to implement. Easy to a certain extent. You have to be familiar with the NLP, Allen NLP. We used Allen NLP's environment to build this. But once you kind of get through that configuration understanding, it's relatively straightforward to build. How does it look? We find, it should be very obvious first, that you get higher overall accuracy with the BERT large. Let me try to orient you. The x-axis is the training set size. So we tested training data with 10 samples all the way to 10,000 samples. And then the y-axis is the accuracy. With BERT large, you observe general higher overall accuracy, which is not unexpected. But what we thought was very interesting is that with transfer learning, you now have new capabilities with extremely limited data. If you look at the performance for naive Bayes, it is not very usable for data points less than 100. If you have less than 100 data points, it's pretty much random, around 50%. But if you're using BERT, you can actually get a decent model with just 100 data points. 100 data points is something that someone can label in a day. Once you label it, you put it in BERT, and you get a working model. Now, we also want to say that these results are based on BERT off the shelf, so we didn't do any further fine-tuning. I'm going to spend the next couple of slides pointing out successes and failures of BERT. BERT gets subtle languages. This is one review that we found. But Valley Girl is one of the few romance films I could sit through. If you use BERT model, it correctly predicts that this is a positive sentiment. If you use naive Bayes, and that's the one at the bottom, it incorrectly predicts it as negative. To understand what the model is doing, we use LIME on top of these model predictions. On the BERT model, we use LIME on sentence level. So if you give it a whole paragraph, it will highlight this sentence is the reason I labeled this review as positive. Now, because there's only one sentence, it's only picking out that one sentence as the reason it's labeling it as positive. Now, if you look at the interpretability results for the naive Bayes, it's saying that it's negative because I don't like, these two words are not good, sit and could. So it doesn't quite make sense. But BERT also gets negation. If I change the sentence into, but Valley Girl is not one of the few romance films I could sit through, BERT correctly predicts that as a negative, and naive Bayes still predicts it as a negative. So that's where BERT is good. Where BERT fails is that it doesn't understand sarcasm. This is a review for a horror movie, and it says, this is without a doubt the most hilarious movie I've ever seen. Well, horror movies are not supposed to be funny, but BERT doesn't understand that. So BERT says, this is positive because of that sentence highlighted in green. Can't really blame BERT for this one. The other thing that it still doesn't quite get is co-reference. Now, some movies, reviews actually refer to multiple movies in the reviews. And this particular one, it's trying to review Showtime, but it's saying that Taxi Driver was a fine film. And BERT says, OK, this is a great review because of this sentence, that was a fine film, but doesn't understand that this fine film is actually not talking about this particular review. That's all I have prepared. I hope it was fun. Thank you.